The quest for a unified theory of physics, often referred to as the theory of everything, has been the holy grail of theoretical physicists for decades. This elusive theory aims to merge the two seemingly conflicting theories, general relativity and quantum theory, governing the world of the immensely large and the infinitesimally small, respectively. This journey has deep roots in history, beginning with Newton's classical physics, which explained the motion of celestial and terrestrial bodies. Fast forward to the beginning of the 20th century, and a patent clerk named Albert Einstein introduced his theory of relativity, painting a new picture of the gravity as a curving space-time around massive objects and revolutionizing our understanding of the universe on large scales. However, Einstein's elegant theory, incredibly successful on large scales, failed in dealing with the microscopic world of particles, which is the realm of quantum mechanics. Quantum theory, introduced by pioneers like Max Planck, Werner Heisenberg, and Paul Dirac, described the world of particles probabilistically. This contrasted with the deterministic world of Einstein's gravity, and hence was born a rift in the fabric of physics that has yet to be mended. The significance of the quest for a unified theory cannot be overstated. It means a complete understanding of the physical world, helping us to answer profound questions like the nature of black holes, the origin of the universe, and potentially even the mysterious dark matter and dark energy that permeates the cosmos. Apart from the pure search for knowledge, practical benefits of such theory could be immense, although it's hard to foresee. We can look back into history for evidence. The unification of electricity and magnetism in the 19th century gave us power generation, motors, wireless communication, etc. Among the most promising candidates for a unified theory is string theory, which postulates that the fundamental constituents of matter are not particles, but rather tiny vibrating strings. Each vibration corresponds to a different particle, elegantly capturing quantum mechanics and gravity in a single paradigm. For one, it predicts additional spatial dimensions beyond the three we experience, a bold claim that hasn't yet been confirmed experimentally. Another contender is loop quantum gravity, which attempts to quantize space-time itself, representing it as a network of tiny loops. This approach is conceptually different from string theory and doesn't require extra dimensions. However, loop quantum gravity struggles to incorporate matter into its framework and has yet to make substantial progress. These attempts have not been without their fair share of consequences, both positive and negative. On the positive side, the quest for unification has led to a plethora of new mathematical techniques, conceptual developments, and indeed entirely new areas of physics like quantum computing and quantum information theory. It has cast fresh light onto the fabric of reality and stimulated a cross-pollination between physics and other fields like mathematics, computer science, and philosophy. Conversely, the increasingly abstract and mathematical nature of these theories has provoked criticism. Some argue that physics has become too detached from its empirical roots, developing theories which, while mathematically beautiful, lack experimental verification. Additionally, the quest for unification has monopolized resources that could be devoted to other areas of science, potentially stunting growth in those fields. Thus, the search for a unified theory of physics traverses a tightrope between grandeur and critique, idealism and pragmatism. It has enveloped the scientific community in a thrilling saga of success, failure, and occasional frustration. As the 21st century continues to unfold, the quest lives on, holding the promise of changing our understanding of reality as we know it.